Okay. All right. So we let A and script B and P0 be the probabilistic model of a trial. So now the sample space, right, of the sequence of independent trial is so the X is actually A infinity, and A infinity actually is the Cartesian product. The Cartesian product of infinitely many copies of the sample space of a trial. Okay? And so an outcome in the sample space can be represented by a sequence of outcomes in A, in the sample space of a trial. Okay. And I think this is very intuitive because, for example, if a trial is to tossing a coin, and so possible outcomes in A is head or tail. So only two possible outcomes. And so if you do a sequence of independent trials, means that you do a sequence of independent tossing coins, then the first time you get either a head or tail. The second tossing you get either a head or tail, etc. All right, so you will have a sequence of H or T. All right, so that is the outcome of the sequence of independent trials. All right, now the sigma algebra F is the smallest sigma algebra of subsets of the sample space X containing the following events of interest. Okay, so let's describe what kind of events are of our interest. It's E and B. So E and B would be, okay, right, so the outcomes of the first n-1 sub-experiments do not matter, okay, so it can be arbitrary outcomes for the first n-1 trials, but at the nth trials, the outcome should be, the nth trial has outcome which it would be in B, okay? So this is at the nth trial, right? And then we don't care of the outcome of the rest trials. Okay, so EN means that we only care about the outcomes of the nth trial. Okay, so that N means here. So the B, all right, and the B is in the script B. All right, it's in here. All right. So B is a member of the sigma algebra for a trial. Okay. Right. So, and for all n1. Okay. So we would like that sigma algebra. We like this kind of event to be event of interest. Okay, this is quite natural, right? Because it is specified by the outcomes, the sub-outcomes in the nth trial. Okay. Okay, so note that EMB is an event whose occurrence, okay, is completely determined by the outcome of the nth trial. Okay, and it is important to know that the atomic event for an outcome of the sequence of independent trial. Right? Is a countable intersection of the events. Okay, and here I would say 3 point, I forgot, maybe I use 3.6, the events in 3.6, i.e. omega 1, omega 2, etc. This atomic event is the intersection for n from 1 to infinity A times Cartesian product with the atomic event for the nth trial. Okay, so this is n equal to 1 to infinity En omega n. Okay. All right. So this atomic event actually is a countable intersection of events of this type. this demonstrates that a sigma algebra F containing this kind of events of interest is big enough. Okay, it's big enough because that this sigma algebra will contain every atomic event. Of course, such a sigma algebra will contain a lot of events, of course, all right? Because that this kind of event of interest, you have infinitely many this kind of event. So, as we have gained some experience last Thursday when we consider the smallest, the sigma algebra generated by n events, right? Remember that? The sigma algebra generated by n events, the size is 2 to the nth power. It's a big one, right? But now you have infinite many such events. So you can think about that the sigma algebra is huge. It's infinite, of course. But and also it will cover all practical events of interest you want to investigate. Okay, so in the future, when we talk about a probabilistic model for the sequence of independent trials, then the sigma algebra will be the smallest sigma algebra containing this kind of event as event of interest. All right, now the last one is the probability function. We have to assign probability function for event of interest in the sigma algebra F. So how do we do that? Okay, so the probability function P from this sigma algebra to plus must, so we require that must have the following two properties. All right? The first one is called time homogeneity. Okay? The time homogeneity is that for this particular kind of event of interest, E and B, the probability, all right, should be equal to the P0B, right, for all B. Right? So I think this is very intuitive because this event depends only on the outcomes in B at the nth trial. And at the nth trial, because we know in each trial we have a probabilistic model here. All right? So for each event in script B, we have assigned the probability P0. Okay, so we should have for this identity. Okay? All right. The second property our requirement is called independence. Because we are studying sequence of independent trials. So for any for any k greater than or equal to 1, and for all n1, n2, nk, and for all b1, b2 up to bk in scope B. Okay, the sigma algebra in a trial. So we have that the probability of En1 B1, so that means that this is an event completely determined by the trial at the n sub 1 time. And the outcome of this trial will be in B1. Okay, so of course this is in this type of event of interest. Intersect En2, right? This is another time at which the outcome of the trial at time N2 is in B2, etc. N sub k, bk, right? Now, and because that they are, we are talking about independent trial. So that we should put independence on that. So this will be En1 B1 times P En2 B2 times P En sub k bk. Okay, so we should have independence, right? Because this event completely determined by the trial at n sub 1 time. This is an event completely determined by the trial at the time n sub 2, etc. Okay, and we assume independent trials. So this event should be independent. Okay, so we must have for this identity, and of course this is by the time homogeneity. This is P0, B1, P0, B2, P0, BK. Okay, so any probability function, if we can create a probability function, they must satisfy these two properties. One is called time homogeneity, the other is called independence. Okay, and it can be shown that there is one and only one probability function on F satisfying the above two properties. Okay, the proof is non-trivial, so I will not go through it in this semester, in this course. Okay, but the fact is that there is one and only one probability functions has these two properties. Okay, so now we have established a probabilistic model for the sequence of independent trial already. So we have figure out the sample space, right? And then we know how to create an appropriate sigma algebra. So we know we collect all events of interest. Yeah. And the last one, we have a probability function satisfying these two properties. We have one and only one. Okay. So we have established SFP as the probabilistic model for the sequence of independent trials. Okay. Any questions? All right, so let's take an example in the textbook. It's a 3.4.h. All right, so our random experiment, it's independent trials consisting of rolling a pair of failed dice are performed. Okay, so we have two dice. You know, each die has 6 faces, right? And so the number will be 1, 2, 3, 4, 5, 6. Now we have 2 dice, a pair of failed dice, right? So we will roll the dice. Okay, it depends on how you play it, you know. And the outcome, now we will describe the sub-experiment, means we will describe the trial, okay? So the outcome of each trial in our investigation is the sum of the dice. Okay, so the sum of the dice. Now we know each dice contain numbers from 1 to 6. If you have dice and you want each outcome, you just sum the 2 dice. So the sum, at least 2, right? 1 plus 1 is 2. At the most is 12, 6 plus 6. Okay. So the probabilistic model A, B, P0 of a trial is, all right, so A is the sample space of a trial, all right, means the set of all possible outcomes of a trial. And because the outcome in our case is the sum of the 2 dice, so that it could be 2, 3, right, up to 12. Okay, so A is the set of integers from 2 to 12. And of course, the sigma algebra will be the power set of A. Okay, and the probability functions for this one, okay, Now, because we have a pair of 4 dice, all right, so when we roll 2 dice, right, okay, then we know that if I'm sorry, the atomic event, as we know, for discrete case, it would be sufficient and necessarily sufficient to specify only the atomic event, right? So the atomic event is that if I is from 1 to 7, okay, because to have, to have 2, 3, 4 up to 5, 6, 7, etc. It's 1 together, and 3, 1, 2, or 2, 1. 4 will be 1, 3, 2, 2, 3, 1. Okay. So the pair means that this is the face of the first die. This is the face of the second die. So if you have 1, 1, you get 2, right? The sum. If you want to have a sum equal to 3, then the appearance would be 1, 2, and 2, 1, etc. And this is 1, 4, 2, 3, 3, 2, and 4, 1, etc. And that would be the case 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. And this is 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. And then 12 will 6, 6 only. So and because all these pairs appear with equal probability, because you have failed dice. So now this is I minus 1 over 36, all right? And 13 minus I divided by 36, which is from 8 up to 12. Okay. Right. So this is by counting. Okay, by counting. All right. Any questions about the probability assignment to atomic event in each trial? Any questions? All right. So now we have the probabilistic model of a trial, all right, and the probability function, the assignment will be here. Now, suppose we let E to be the event that an outcome of 5 appears before an outcome of 7. Okay? So suppose E is the event that an outcome of 5 appears before an outcome of 7. Of course, this outcome would be outcome of a trial, right? So an outcome of 5 appeared before. So, for example, okay, 2, 3, 5, 6, 7, 3. This outcome will be in the event. So this outcome of sequence of trial will be in this event. Why? Because 5 appear before 7. Okay? But another outcome. Okay, okay, this outcome is not in the event. Why? Because 7 appeared before 5. Okay? So this event contains infinitely many outcomes, right? This event contains infinitely many outcomes. You are not able to describe it by enumeration, right? Okay. Another, so, and you might want to find the probability of this event, right? How can you do so? Right? You may want to find the probability of this event, E. But this event is not as simple as this type only. Because events of this type completely determined by the trial at the nth time. But you can see this event does not determined by a trial at any time, right? Any time instant. Okay. Let's see the event that no 5 or 7 appears, okay, on the first n-1 trials, okay, and a 5 appears on the nth trial for n from 1 to etc. Right? So now we consider f sub n is an event that the first n-1 trial, no 5 or 7 appears. But at the nth trial, the outcome is 5. Okay? So take a look at this one. For this outcome, you will see that this outcome, right, is in F, what? 3, right? Is that correct? Because this is time 3, and so time 1 and time 2, no 5 or 7 appears. But at the time 3, 5 appears. Okay, so this is in F3. And how about this one? How about this one? Of course, this one cannot in any Fn, right? Why? Because 7 appeared, even though 4 and 6, the first 2. So, but this time 7 appears already. Okay? So you can see it for any, right? It is not in there. Okay. All right. So now, note that Fn is an event which is easier to study, more easier than E. Why? Because we can describe Fn can be described as E1 such that A of phi 7 complement. Okay? So at the first time, at the first trial, that phi and 7 cannot appear. So this is a complement of phi and 7. Intersect up to En minus 1 of 5, 7 complement. Of course, this complement is actually A minus 5, 7. Because at each trial, the sample space is A. Okay? Alright, so that at the first N minus 1 trial, this you must the event, all this event occurs. And the last one, for nth trial, you have this atomic event for the nth trial. Okay, and we don't care about the after trial. All right, the first coming trial, we don't care about that. All right, so you see that this event can be determined by n simple events of interest here. Right? Okay, so they can describe by the simple events of interest. And from here, so the probability of Fn actually we can compute it, right? By what? By the two properties, independence. Oh, sorry. Sorry, I have typo errors. So by independence and the time homogeneity, that this is actually equal to, what is that? It's P0, 5, 7 complement times P for n minus 1's power and the P0 of 5. Okay? And this is what is that? This is 26 over 36 and minus 1, and this is 4 divided by 36. Okay? Okay, so you can determine or compute the probability of Fn immediately. Okay, by the two properties, time homogeneity and independence. Okay, here is equal to this one. Okay? Now, it can be seen that Fn's are mutually exclusive. So they are disjoint. They are mutually exclusive of each other. And so their intersections, the intersections are empty set. So E, and you can see that is the disjoint union. The event E is the disjoint union of Fn. Okay? So that by the countable additivity of the probability function okay, PE is the sum of the probability of Fn. Okay, and now we have a serial sum because we already know that this is 26 divided by 36 n minus 1, 4 divided by 36. Okay, and this is power series, right? And so the result is 2/5. Questions? So this example demonstrates some key features of computing the probability of an event, right, in the random experiments of a sequence of independent trials. So usually you have to find some related events which can be determined by finitely many events of interest like this one. Okay, once you just like the Fn here. Okay, now then you can apply the two properties, the time homogeneity and the independence property, to compute the Fn. Okay, and finally, the target event can always express as the joint union. Okay, and so you can apply the counterballitivity of the probability function to compute the probability of the target event. Okay, so this strategy is universal. Okay. Okay. Now conditional probability. All right. This section will develop a theory to treat conditional probability given an event f to be a probability function. And so that will be stated in the first proposition. So for any event f in the sigma algebra, f p, the conditional probability of any event given event f have occurred is a function from f to r plus which satisfy the three axioms of a probability function. Okay? Alright, so let's give a proof. Alright, if the probability of the event f is 0, we have, by definition, we have defined conditional probability of an event E given that event f have occurred is probability of E for all f. Okay, and so that the probability, the proposition follows immediately. Right? Because the conditional probability is equal to the unconditional probability by our definition. And this probability function is already a probability function, so it must satisfy the three axioms. Okay? So we now assume that probability of f is greater than 0. Okay? Now, since P, by definition, the conditional probability of an event E given event f has occurred is P of the intersection of E and F divided by probability of F. Okay, right? And we know that probability function P always non-negative valued. Okay, this one, and so P of E F is greater than or equal to 0. Okay, so which is axiom number 1, right? So conditional probability always greater than or equal to 0. Now, also, since x intersect f is equal to f, okay? S is the sample space. The total event intersect f is also equal to f. So we have the probability of x given f. Okay? So the conditional probability of the total events given the event f has occurred. This is probability of x. So this is 1. Alright, so which is axiom number 2? Okay, so the conditional probability of the total event given that event f has occurred is equal to 1. Okay, so that is this axiom number 2. Now, for a sequence E1, E2, etc. of mutually exclusive event. Alright, so if E1, E2 is a sequence of mutually exclusive event, then E1 intersect F, E2 intersect F, etc. Okay, it's also are also mutually exclusive. And then, okay, so the disjoint union of En. So the conditional probability of the disjoint union of En, given that event F has occurred, by definition, which is intersect F. Okay. And now, by the distributive law, we have the union okay. Yep. Now, because this is the disjoint union, right? So by countable additivity of probability function, so this is, sorry, this is infinity. F here. Okay, and summation divided by PF. Okay. Finally, so the conditional probability of the disjoint union of En, given the event F has occurred, is equal to the sum of the probability of the conditional probability of En, given that event F has occurred. Alright, so this is axiom number 3. Okay? So we have checked the 3 axioms. Okay, so that the conditional probability, all right, is as a function from the secant algebra to R plus. It's a probability function. Okay, maybe so that's the P all right. Okay, so now it's clear that originally we have a probability function P on the sigma algebra F. Now for each event F in the sigma algebra, we can create a probability function, okay, by conditioning. And because you have infinitely many in principle, or a lot of F, right? So actually you create many different probability function on F. They are all probability function and satisfy 3 axioms. Yes, please. Yes. Oh, no, no, the same. Yeah, yeah, I'm sorry, the same. Yes. Sorry. Yeah, because the x, you know, the sum space here is S, and this is F. Because F, an event always a subset over S. Okay, so the intersection of F and S should be equal to F itself. Yeah, thank you. I'm sorry. Yeah, I don't mean to change the style of the character. I'm sorry. Yeah. Other questions? Okay, so you have the concept that once you are giving a probabilistic model for a running experiment, means some space sigma h by f and a probability function p, then actually you can induce many, even infinitely many different probability functions. If you consider conditional probabilities given a fixed event has occurred. Okay, so indeed for different f, you may have different probability functions. So you have a lot of probability functions at hand. Okay. Okay, so let's take a break of 5 minutes, all right? Okay. All right. We sometimes denote conditional probability as P sub f of E. Okay. Right. This notation is to emphasize that conditional probability is a probability measure. Okay? So if we want to emphasize this point of view, we sometimes use this notation. Okay. Okay, so for example, from proposition 2.4.3 in chapter 2, we have P F E1 union E2. Okay, so for condition probability, all right, so you want to know E1, E2 may not be mutually exclusive, just arbitrary, right? So this is PF E1 plus PF E2 minus PF E1 intersects E2. All right. So actually, this is the simple inclusion exclusion principle or identity, right? Okay. But and this one actually is equivalent to. So when we write it down in this way, this is equivalent to what? To P E1 union E2 give condition F is equal to minus P E1 E2 condition F. Okay? So any identity, including the inclusion, exclusion identities or inclusion, exclusion inequalities, okay, all these properties in chapter 2 can be applied for conditional probabilities. All right? And that is very useful in many computation. So now you can see you have extended your horizon a lot. Okay, you have extended your horizon a lot. Now, now I want to drive your brain. Okay. Right, if P sub Fg, right, that means that this condition probability is greater than 0. So we define the conditional probability P F E G by. So you define conditional probabilities on conditional probability. Okay? This is two label. Actually, you can have n label. Think about C language or Python, any language. You have recursion, right? You have recursion, and it sometimes drives you crazy, right? Okay. We have the same situation here. We have the same situation. So, okay, so how do we do the, okay, so definition. Okay, because we want to put this conditional probability in the denominator, so we require that this must be positive here. Okay, and of course, if the conditional probability is 0, all right, so we define, again, we define PF E given G to be PF E. Okay, as before. Okay, so now give us several supplemental propositions not in the textbook. Okay. Okay, for any events E, F, G, we have PF E intersect G equal to PF of G times PF of E G. Okay, this is the same as we have done for P before. Okay, but now because conditional probability is also a probability function, so we have that to find this conditional probability of the intersection of E and G given the event F has occurred is actually equal to the conditional probability of G given F has occurred times the conditional probability, all right, of event G given event of conditional probability of event E given event G have occurred and given event F has occurred. All right? Maybe I write here. Sometimes I usually think if you are a good programmer, you should good at probability theory. Why? Because the basic thing is logic. Okay, the basic thing is logic. Okay. if probability of F intersect G is greater than 0. Okay, now suppose that then now I want to interpret because this is it involves two levels of conditional probabilities, right? But this two level conditional probability can be written in the following way by one level conditional probability. So what is that? Okay, this one. And so, and with that, so this is crucial, okay? So this is crucial. Okay, and so that this is okay, and so by symmetry, this is becomes to okay by symmetry. But we have this result only if the probability of the intersection of F and G is positive. It's crucial. Okay? All right, so proof. Okay, so since and okay, so we had the identity before, right? So we have F has positive probabilities, G has positive probabilities, conditional probability of G given F is positive, conditional probability of F given G is also positive. Okay, so we have positive, positive, positive here. So now, P of E divided by G, by our definition, which is P, E, G here. This is by definition, okay? The reason is the conditional probability of G given F is positive, so we can put into the denominator here. All right, and what is this? This is okay. So now this is the same. Okay, and by the definition of conditional probability in the first label, okay, so this is okay here. Now we are safe because everything here, PF is positive, all right? And P of G intersect F is positive. So we don't worry about that. Okay, and now we can cancel P of F. So we have P of E intersect with G, intersect with F, and this is P of G intersect F. Okay, and so this is P of E given G intersect F. Okay, and this is P G intersect F of E. Okay. All right, and similarly, PG of E given F is equal to PE given G intersect F. So this is P of G intersect F of E. And we have done. So two-level conditional probabilities is equivalent to one-level conditional probabilities if this probability is positive. So remark, when the probability of F intersect G is equal to 0, proposition 3.5.b may not be true. Okay, so you have to be very careful. You have to be very careful because when we define conditional probabilities, we artificially to define this identity when this probability is 0. That will give you some trouble. Okay? That will give you some trouble. Okay. So you have to be aware of that. So to convert two label or three label and labels of conditional probabilities into one label conditional probabilities, be aware that this precondition here. Always check that. Right? This one, this event has positive probability. Okay, don't forget it. Otherwise, sometimes you will get the wrong answer. Now, for proposition to 3.5.c, if the event F has positive probability to occur, then okay, then the conditional probability, all right, of E intersect G given the event F has occurred is equal to, first of all, the conditional probability of event E given F times the probability of conditional probability of G. Oh, okay, sorry. It's better to write it this way. First of all, G, and then F. Okay. You may use this identity before, for example, in high school. But you may neglect this requirement that the probability of F should be positive. Otherwise, you may have an artificial result. Okay? Oops, sorry. All right, so let's see proof. So if the probability of G intersects F is positive, this one is stronger than this one. Because if this intersection has positive probability, then F has positive probability. Why? Because event F is bigger than this event. So this probability always greater than or equal to this probability. Right? So if we have this one, this proposition follows from propositions from the previous two propositions, 3.5 point A and 3.5 point B. Okay. So you can see that. Okay. From that. Okay. So now if proposition of equal to 0, then probability of E intersect G given F, which is equal to probability F, probability of E intersects G intersects F. Okay. So this, all right. So this conditional probability by definition, and the reason why we can put P of F in the denominator is because we have now this is positive. Okay. But this is less than equal to probability of G intersects F, P of F. Why? Because this event is smaller than this event. Okay? And this is 0 because the numerator is 0. So this is 0. Okay? So this, and of course, probability always non-negative, right? So that given F is 0. Okay, so this is 0. Okay, but so this is 0. How about this one? And the P of G given F, so this is P of F, P of G intersect F, and this is 0. Okay, so we have 0 equal to 0 times something. So we conclude that P of E intersect G given F, which is equal to 0, is equal to P of G given F times P of E given G intersect F. Okay. This one, by definition, is P of E. Why? Because that the probability of G intersect F is 0. So this is. Okay. Then the P of E may not be 0, but that's fine because this is 0 already, and this is 0 already. Okay, so we have done. All right, so proposition 3.5.b and proposition 3.5.c are very useful. Very useful. Okay, but their validity depends on the different requirements. For this one to be true, we require that the probability of F intersect G should be positive, and for this one, we require only probability of F is positive, has positive probability. Any questions? Now we can extend our decomposition formula to conditional probability. So for a partition, say G1, G2 up to Gn, for a partition of the sample space, so we have the conditional probability of E. E can be arbitrary, okay? Arbitrary event in the sigma algebra F. Given the event F has occurred, x equal to P of F, E intersect Gn or Gi, okay? Because it's a partition, all right, and by the conditional, the two-level conditional probability, this is PFGI and PF E given GI. Okay, this is straightforward because P sub F, this condition probability given event F has occurred, is also a probability function. So it has so this is we call decomposition formula, right? For conditional probability. Okay, so this is conditional formula. And if So if the probability of F is greater than 0, so we call this 3.8. 3.8 is equivalent to, right, so let's write down. Okay. Summation I from 1 to n, probability of GI given F, probability of E given GI intersect F. Okay. Since PF GI PF E given GI, so this is PF E intersect GI. Okay. So PF is PI. This is for proposition 2.5.8. Right? Because P sub F is a probability function. So this is proposition. Okay, and so this is P of E intersects GI given F. Right? So we write this notation. And for this one, by proposition 3.5.c, because we have P of F is positive. So this is equal to P of GI given F and P of E given GI intersects F. Okay? So this together, PF GI, PF of E given GI is equal to P GI given F times P of E given GI intersect F. And so this is proposition 3.5.c. Okay, so the only requirement is this one. We do not need to require this is stronger condition. Okay? We don't need to require this is stronger condition. The reason is we consider this product together. Right? So this is equal to this one. So if the probability of dependent F is positive, then the decomposition formula becomes to this formula. This is very useful. Okay? And the only requirement is that the event F has positive probability. Any question? Now, we have consider conditional probability under conditional probability, right? Two-level conditional probability. Now, we now define independence under conditional probabilities. Okay, so two events, E1 and E2, are said to be conditionally independent given an event F, given that an event F has occurred. Okay, if use the conditional probability measure, if E1 intersect E2, so this conditional probability is equal to the product of the respective conditional probability. And equivalently, P E1 intersects E2 given F is equal to P E1 given F, probability of E2 given F. Now proposition 3.5.d. If E1 and E2 are two conditionally independent events, given F, all right, then PF E1 given E2 is equal to P PF given E1. Okay, so two-level conditional probabilities equal to one-level conditional probability. Okay? And by symmetry, E2 given E1 is PF of E2. Okay? Okay, so this is just a direct extension from our probability, because this is true for any probability measure. Okay, for any probability function. And conditional probabilities, as we just proved in proposition 3.5.1, that it is indeed a probability function. Okay, so this must be true. Furthermore, if the probability of E1 intersects F is positive, then probability of E2 and given E1 intersect F is equal to probability of E2 given F. And if probability of E2 intersect F is greater than 0, then probability of E1 given E2 intersect F will be equal to probability of E1 given F. Alright, the requirement, why we require that? Because we will apply, this is by proposition 3.5.b, because B is required there. Okay, so this is from proposition 3.5.b. Remember, we should have E1 and E2 are two conditionally independent events given F. Okay, so that is the precondition. So if E1 and E2 are two conditionally independent events given F, and if this is true, if this is also true, then the conditional probability of E2 given E1 and F, right, is equal to the conditional probability E2 given F. So you can eliminate the effect E1. Okay, the reason is E1 and E2 are conditionally independent, so you can remove the effect of E1. When you consider condition also based on F. And if we have this condition, the intersection, the probability of E2 and F is positive. Now we can, for this conditional probability, we can eliminate the effect of E2. Okay? Right. So now you can see some of the formality. If you use conditional probability, regard the conditional probability as a probability function, then everything is true as before. Okay? Just like an unconditional one. Okay? But if you want to put, so this involves two label conditional probabilities, okay, here. But if you want to express everything by one label conditional probabilities, you should be very careful, because some preconditions must be satisfied first. Okay? Because one label condition probability is much more simpler than two label or three label or n label conditional probabilities. Okay. Okay. I almost run out of my time, so I think I can't discuss more examples right now. So I will ask you to read the examples in the textbook. Okay, but applying the concept I introduced today, okay, because propositions A, B, C, D are extra propositions, okay, not in the textbook. Remember, only numerical 1, 2, 3, 4 are propositions in the textbook. If the alphabetical propositions are propositions I provided as to you, right? So they are additional propositions. Okay, so that is the for two conditional independent events. So now I have very limited time. So the n events E1, E2 up to En are called conditionally independent given event F if for 1 less than equal to I1, less than I2, less than IR, less than equal to N, and R is from 1 to N, that the conditional probability of EI1 intersect EI2 intersect EIR is equal to the product of the conditional probabilities. Or equivalently, probability of EI1 intersects EI2 intersect EIR given F is equal to probability of EI1 given F times probability of EI2 given F times probability of EIR given F. Okay, and if I from 1 to N are conditionally independent given an event F, then each EJ will be conditionally independent of any event in the F E1 up to EJ minus 1, EJ plus 1, En. An event generated by EIs except EJ. I think last Thursday I used G, but I decided to change my notation to use F, okay? Use F. Okay, so I encourage you to correct the script later from G to F. Okay, because I prefer F. So later on I will use F. So this sigma algebra is the smallest sigma algebra generated by n-1 events. Okay, so members in this sigma algebra are events formed by this n-1 events using logical operators, not and or. Okay, that's all. Not and or, not and or in any sequences, in any order. Okay. Anyway, so they will be conditionally independent of any event given F, of course. All right, so we have the same. All right, so that is for a finite number of events to be conditionally independent. How about an conditionally independent for infinite collection of events? An infinite collection of events is called, sorry, conditionally independent given an event F if every finite subcollection of those events is conditionally independent. Given F. Okay, so that is the general case. Okay, and the last one. Okay. In a random experiment, consisting of a sequence of sub-experiments this sub-experiment are called conditionally independent. Given an event F with the probability of F is positive. If given the event F, the outcomes of any group of sub-experiment have no effect on the outcomes of the other sub-experiment. Okay. So formally, if En is an event whose occurrence is completely determined by the outcome by the outcome of the nth sub-experiment. For n from 1 to etc. Then the sequence of event, okay, is a collection of conditionally independent events. Given the event F. Okay. So to establish the probabilistic model for such a sequence of conditionally independent sub-experiments given an event F, then we use the same probability model by using conditional probabilities given F. Okay, as we have done at the beginning of today's lecture. Okay, that is similar. Okay, as you can see, all the concept of independence can be extended to conditional probabilities. Okay, they are just a straightforward extension. The only difference is that instead of using the original probability function P, we are using conditional probability function given the event F. That's all. Okay, and everything can be found. Okay, so you can apply one-level conditional probabilities to do it. And the many running experiments by its structure, by its nature, okay, you can assume that the sub-experiments are conditionally independent. Okay, as you can see some of the examples in the textbook. Okay, so I have to stop here because, and I hope you embrace some of the spirits of conditioning as well as independence. Okay, so as you see, by using logical reasoning, you can extend the horizon to unlimited region. Okay. Okay, so always thinking probabilistic problems by logical reasoning. All right. Before you do any computation. Any questions? Okay, so I'll stop here and see you next Tuesday.